Assalamu alaikum dear students. Welcome to multivariable calculus course. We have already defined vectors in 2 and 3 dimensions and learned how to compute magnitudes, unit vector and vector operations. So today we'll study one of the most useful operations involving vectors, and that is dot product. Dot product allows us to measure how closely two vectors point in the same direction. It also provides a powerful way to find angles between vectors and compute vector projections. So by the end of this lesson, you will be able to compute the dot product of two vectors, interpret the geometric meaning of the dot product, find angles between vectors, determine whether vectors are perpendicular, compute scalar and vector projections, applications of projections to practical problems. So let's begin. If we have two non-zero vectors u and v, and angle between these vectors is theta, then dot product of u and v is defined by magnitude of u times magnitude of v cos of angle between them, and it is denoted by u dot v, where theta lies between 0 and pi. If theta is 0, then u dot v is simply the product of their magnitudes, because cos 0 is 1. And if the angle between the vectors is pi, then this dot product becomes negative of the product of magnitudes of the vector, because cos pi is negative 1. So you can see if theta is 0 or pi, the vectors u and v are collinear. And if angle between the vectors is pi by 2, that is if the vectors are perpendicular to each other, then u dot v, that is dot product of u and v, is 0, because cosine pi by 2 is 0. So we can see that dot product can have positive sign, negative sign and 0 value as well. So dot product is negative when theta is greater than pi by 2, and this is positive if theta lies between 0 and pi by 2. At pi by 2, you can see that dot product is 0. So let's know how this matters. The dot product measures how much one vector points in the direction of another. So large positive value indicates similar directions, 0 indicates perpendicular directions, and negative value indicates opposite tendencies. So if we have two vectors in component form, then dot product of these two vectors is defined by sum of product of corresponding components of the vectors, irrespective of the fact that vectors are in space or plane. In both the cases, dot product is defined by the sum of product of their corresponding components. Dot product is also referred to the scalar product, or sometimes it is called inner product as well. So there are few results related to the dot product. We know that this I is the unit vector along x-axis, and it has components 1, 0, 0 if it is in space. So dot product of I with I can be written as the dot product of these two vectors. And using component definition of dot product, we can see that this is equal to 1 plus 0 plus 0, and this is 1. Or if we use angle definition of dot product, then we can see that I and I has same direction, so the angle between I and I is 0. So cosine 0 is 1, magnitude of I is 1, magnitude of I is 1. So answer is again 1. Similarly, we can prove that j dot j is 1, k dot k is 1. We can also conclude that dot product is commutative. U dot v is equal to v dot u because angle will remain same. There are few properties of dot product. If we have three vectors u, v, w and c be a real number, then u dot v is 0 implies either u is 0 or v is 0. If both are not 0, non-zero vectors, then they are perpendicular to each other. Dot product is commutative. Similarly, distributive property holds for dot product. U dot v plus w is equal to u dot v plus u dot w. And if c is a scalar, then scalar multiple of u, that is c u dot v, is c times u dot v. Now angle between two vectors. So this definition of dot product actually helps us find angle between the vectors. If we have two vectors, angle between them is theta, then this definition gives the angle, cosine of angle between them equals u dot v divided by u magnitude times v magnitude, and theta can be found by taking cos inverse of this, where theta lies between 0 and pi. And this is actually useful if we have vectors in component form and we are required to find angle between them. So if we have u and v with components x1, y1, z1, x2, y2, z2 respectively, then u dot v is defined by the sum of corresponding product of corresponding components. Then angle between them is equal to this, where u magnitude would be x1 square plus y1 square plus z1 square whole square root, and v magnitude would be x2 square plus y2 square plus z2 square. Now, projection of one vector upon another. So there are several situations when it is required to find out how much of a vector is applied along a given direction, or what is a scalar component of one vector in direction of the other vector, or how parallel two vectors are. So dot product gives us the answer of all the questions. Suppose we have two vectors u and v, and angle between the vectors is theta, and we are required to find out projection of vector u onto vector v. So you can imagine shining a light perpendicular to vector v. The shadow of vector u on the line determined by vector v is projection. So its length is scalar projection. So we are currently trying to find out the scalar projection of u onto v, and this length can be calculated with the help of this right angle triangle. So we know that this length divided by magnitude of u is cosine of theta. So this length is magnitude of u times cosine theta. So projection of u along v is magnitude of u times cosine theta. So if we are required to write it in terms of dot product, then divide and multiply this by v magnitude. Now numerator becomes u dot v and denominator is v magnitude, right? So this is the projection of u along v. Similarly, we can find projection of v along u, and for this we have to throw light perpendicular to vector u, and the shadow of vector v on the line determined by vector u is the projection. So this can be represented with this formula, V magnitude times cosine theta, and we can also write it in terms of dot product u dot V divided by u magnitude. What if we are required to find vector projection? So for this, we have this projection of u on V. So vector projection of u on V is equal to u dot V. This is actually the length of the projection. This scalar quantity represents the magnitude of the projection. So we know that its the direction is the direction of V. So we have to, in order to represent its direction, we have to have unit vector in direction of V. So this is the unit vector. So when you take magnitude, this will not affect on the value. Or you can write it as u dot V divided by V magnitude square V. So this is the vector projection of u on V. Similarly, we can find vector projection of V on u, and that would be u dot V over u magnitude square times u. So this is vector projection of V on u. Now, if we have a vector OP with the components x, y, z, and let this vector make angle with x-axis equals alpha, with y-axis its angle is beta, and it makes an angle gamma with z-axis, then cosine of all these angles are called direction cosines of vector. And these angles are called direction angles of this vector. So we can find the cosine of all these angles with the help of angle between the vectors, because you can see that alpha is the angle between vector v and vector I, the unit vector along x-axis. So if v has the components v1, v2, v3, that is v is equal to v1i plus v2j plus v3k, then cosine of alpha is equal to v dot I divided by v magnitude times I magnitude. Since I is the unit vector, so I magnitude is 1, and v dot I is in fact 1i, and rest of the components are 0. So dot product is the sum of product of corresponding components. So v1 times 1 plus 0 plus 0. So this becomes v1. So cosine alpha, that is the cosine of this angle, is equal to v1, that is I component of v divided by v magnitude. Similarly, cosine beta is j component divided by v magnitude. And similarly, cosine gamma is v3 divided by v component. And if we square all these cosines and add them, then we have, let's square all of them. Cosine square alpha is actually v1 square over v magnitude square. Similarly, this is its cosine is v2 square over v magnitude square. Similarly, square of cosine gamma is v3 square, v magnitude square. So if we add all these, we'll get v1 square plus v2 square plus v3 square, which is equal to the square of magnitude of v. So this is v square over v magnitude square, and this is equal to 1. So this is the result. Cos square alpha plus cos square beta plus cos square gamma is 1. Now, decomposition of vectors into orthogonal components. And for this, if we have a vector v, you can see this figure, we have a vector v, and we have two perpendicular vectors v1, w1 and w2. E1 is the unit vector along W1, E2 is the unit vector along W2. And this means E1, E2 both are perpendicular to each other and they are unit vectors as well. And our target is to write V as K1 E1 plus K2 E2. So this is decomposition of vector in terms of orthogonal vectors. So our target is to find values of K1 and K2. For this, take dot product of V with E1, and this will give us K1 E1 dot E1 is 1 because this is a unit vector, and K2 times E2 dot E1, since E1 and E2 are perpendicular, so that will be 0. So K1 is V dot E1. Similarly, we can prove that K2 is equal to V dot E2, and just plug in the values into this expression. We have V is equal to V dot E1 E1. This is scalar and this gives the direction, this is vector, plus V dot E2 E2. So V dot E1 and V dot E2 are the scalar components along E1 and E2 of V, and V dot E1 E1 is and V dot E2 E2 are the vector components of V along E1 and E2 respectively. So if theta is the angle between V and E1, this, since E1 and E2 are perpendicular, then this angle will be 90 minus theta or pi by 2 minus theta. Then V dot E1 can be written as, in terms of theta, V magnitude times E1 magnitude, because E1 is the unit vector, so that is 1 cosine of theta. Similarly, we can write V dot E2 is equal to V magnitude times cosine of 90 minus theta, and that is sine of theta. So V magnitude sine of theta. So V can be written as, so just replace V dot E1 and V dot E2 by these values in this equation. So V then becomes V cos theta, V magnitude cos theta, E1 plus V magnitude sine theta, E2. And angle between E1 and E2 is pi by 2, that is they are perpendicular to each other. So this is the decomposition of vector into orthogonal components. There is an example of decomposition. If we have V equals to 2, 3, matlab 2i plus 3j, and E1 is 1 over square root 2, 1 over square root 2, E2 has components negative 1 over square root 2, 1 over square root 2. Find the scalar components of V along E1 and E2, and the vector components of V along E1 and E2. We just learned how to find scalar component. V dot E1 is the scalar component along E1, V dot E2 is the scalar component along E2, and similarly V dot E1 is the vector component along E1, and V dot E2 is vector component along E2. So this is how we can decompose a vector V into its orthogonal components. So that's all for today. See you next time. Take care. Bye.